SwayamPrabha. Digital India. Educated India.
In the previous set of lectures, we determined the shape of a static meniscus using two different approaches. One was the force balance approach, and the other was an energy minimization approach. In particular, in the energy minimization approach, we showed that there is a quantity which we can conveniently call the Lagrangian, and this quantity has to satisfy the so-called Euler-Lagrange equations. This quantity Lagrangian, or a function f as we called it, is the sum of the surface energy and the gravitational potential energy. In many other examples in capillary statics, we will encounter problems where we will have to solve a minimization problem subject to some constraints. I am showing you two examples on your screen. In the left panel, you see a soap film that is formed by taking a metallic cube like this and dipping it into a soap bath and pulling it out. Immediately what happens is you form a soap film. The soap film is far more intricate than you may have imagined. For example, the soap film is not the film that forms on the surface of the cube, but rather it's a film that starts at the edges of the cube, and then all these different shapes, basically all these different surfaces sort of converge towards the center of the cube. They can either meet at a point, or they could meet on a small plane, or they could meet at the edges of at the vertices of another cube. Now this is a constraint problem, because what is the problem statement for a problem like this is determine the shape of the soap film subject to the constraint that the soap film meets the edges of the larger cube. Now you could also have a constrained minimization problem for a sessile drop. A sessile drop is a drop that's sitting on a horizontal plate. Now you could again ask, what is the shape of the droplet subject to the constraint that the volume is prescribed. Now how do we address these problems? In the previous examples, we did not see a problem, we did not have an issue with providing a constraint. Now we have to incorporate this constraint. Now to do this, we need to use the so-called method of Lagrange multipliers, and that's exactly what will be discussed in this lecture. We will be digressing from capillary statics, and I'll give a very brief introduction to this method of Lagrange multipliers, and we will be employing this method in the subsequent lectures. So what exactly is this method of Lagrange multipliers, and how do we use it? Now let's take a very simple problem before we do this. So I am just drawing a simple function. Let's say I take a coordinate system, 2D system like this, or I can just say this is f of x versus x, and I have some arbitrary function which may look like this. Now I could ask a question, which is, what is the maxima and the minima of this f of x between 2 points x1 and x2, right? This is a well-posed problem. I could easily determine this by doing the following. I can find out where the slope of this function goes to 0, and if I do this, I basically get 2 points here, and at both these locations the slope as indicated by the tangent is 0. So in other words, we will be employing this tangency condition, right? And this tangency condition will tell us where the function has a maximum or a minimum. Okay, so essentially this tangency condition is essentially like a derivative test. Okay. Now at these points, the function, it's a function of a single variable. So I can just say df by dx is 0 at both these points. Okay. Now how can I extend this idea to a function with a constraint? Let's first take a look at a function with two variables. Okay. So here on the left panel, what you see is a Gaussian function. So the Gaussian function is defined like this. This is a function of two variables, x comma y. And then you have this function is defined as minus x square plus y square. And the moment you look at a function like this, I ask where is the maxima or minima? Again, that's a well defined problem because there is a global maxima and the global maxima is at this peak. And at this peak, the derivatives, now it's a function of two variables, the partial f partial x is 0 and partial f partial y is 0, which means that the tangency condition is now a plane. Okay, so we have different levels of this height. So z is basically vertically up. So I have different planes of z. Okay, and I'm asking, find out the plane which basically just touches this function, this hump that I have shown here. Okay, and that is the plane, the value of z of that horizontal plane which just meets this surface or becomes a tangent plane to this surface f of x comma y is the maximum. Okay, it could also be a minimum, but the same idea works for a minimum as well. Okay, in this case we have a global maximum. Now let's consider another example that you see on the right panel. In this case, the function f of x comma y is x plus y. Now clearly there is no global maximum because as you increase x or y, then the function keeps increasing unboundedly. And the colors indicate the magnitude of the function. For example, red means larger values of f and blue means lower values of f. Similarly, as you keep decreasing x and y, the function will keep decreasing in its value. So clearly, a question like what is the maxima or the minima of this function f of x comma y does not hold much value. Okay, but rather a meaningful question could be, on this plane, if I have a different curve, meaning if I'm staying on a constrained curve, and this constrained curve is, let's say, this curve here, if I'm going along this constraint, the direction is not very important. If I'm going along this curve, I could ask, what is the value of the maximum? Okay, now there are a couple of things to notice here. Now, just looking at the figure, you can immediately say that, look, this is the maximum and this is the minimum. Now, what is this? Now, what is the what's the key idea here? The key idea is that you have to first of all stay on the function f of x comma y, which means that you are on the surface. Okay, that's colored surface, and then you also have to stay on the constraint curve. Okay, shown on with the black line, and you have to determine and now there could be an infinite number of points where the curve and the constraint meet. You want to find out what is the maximum of all such collection of points. Okay, so let me illustrate this again a bit more graphically where this tangency condition comes in, and we'll return to this graph. Okay, now let's say I consider a function which is defined as f of x comma y is some constant c. Okay, so I want to first make contours of this function. Okay, the way I'll draw contours of this function is I'll say that maybe there is a maxima, global maxima somewhere here, but these I can make contours. So contours are, remember, lines, iso values of this function, which means that along a given curve, the values of the function are constant. So each of these curves correspond to specific values. For example, here I could be having, I'll just use shorthand notation, I could be having f equals d1, f equals d2, f equals d3, f equals d4. These are all some known constants, right? Now, I am also having a constraint function. This constraint function, so this is my y and x. This constraint function, I'll show it in red. So let's say I have a constraint function which is some function in this form. This is my constraint function. This function here is g of x comma y. So now we have a constraint function g of x comma y equal to 0. So what's the basic idea of determining the extremum, the maximum, minimum? The idea is is as follows. I want to move along this constraint. I want to take a walk along this constraint. As I walk along this constraint, I first thing that I want to make sure is I want to satisfy the function f of x comma y equal to c, and those are given by these contours. Okay, and I also want to be on the constraint. So I can easily identify several points. For example, this is one such point, this is another point, this is a third point, and so on. Several. You could have an infinite number of points because this is a smooth curve and there are f of x comma y, there are several contours. I've only shown a few specific contour values. Now let's basically number them 1, 2, 3, 4, and 5, and so on. Now all of these points, 1, 2, 3, 4, 5, these points that I'm showing, all of them satisfy the two essential requirements, which is f of x comma y equal to c and g of x comma y equal to 0. But what are we actually trying to do here? The problem statement that is actually given to us is maximize f of x comma y subject to g of x comma y equal to z is equal to 0. I've taken it to be 0, but it could be any constant. It doesn't really matter. Okay. Now, the first constraint, it's where the key word in this case is we want to maximize. The question is we want to ask which of these quantities maximize. Now, one thing I should have emphasized and I forgot to mention is these isocontours are drawn in such a way that d1 is greater than d2, is greater than d3, is d4, and so on. Okay, so different isocontour values of different values. Okay, now notice that if you walk along this constraint, that is g as shown in the red arrow, then when you maximize f of x comma y and you're also on the constraint, then you should just barely touch, meaning the constraint g of x comma y should barely touch, it should just barely kiss the contour, one of the contours of f of x comma y. For example, in 1 and 2, you can clearly see that if you hit 1, the point number 1, where g of x comma y equal to 0 and f of x comma y is equal to constant on that 1, you could ask, you shouldn't stop there, because if you clearly go a little further along the contour, along the constraint g, the value of f is increasing. So clearly 1 cannot be a maximum. Okay. What about 2? You have the same issue again, because if you continue along the constraint from 2, if you proceed a little further from 2, the value of f is again changing, it's increasing. So you want to reach a point where the value of the function is not changing anymore. Okay, the value of the function is not changing anymore. Okay, and this will happen when the contour curve of f and the constraint curve basically barely touch each other, which means that they have a common tangent. And I'll show the common tangent with the orange curve. Maybe I'll show it with a blue curve. The common tangent is, this is my common tangent. Now what does a tangent mean? The tangent means, let's say that the gradient for f is shown here. That's the gradient of f. Okay, it's a vector, and let's say the gradient of G is this. If both the curves have a common tangent, then the gradients basically have a relationship with each other. This should be G. So if the two curves touch each other, curves that is contour of f of x comma y equal to c and the constraint g of x comma y equal to 0, if the two curves have a common tangent, then gradient of f, which is a vector, is related to gradient of g with a constant lambda. Why do we have a constant lambda? We have a constant lambda because the gradient of f and gradient of g need not point in the same direction and need not have the same magnitude. They have the same overall direction in the sense that they are either pointing in the same direction or they are in opposite direction. Okay, but they need not be of the same size as well. Okay, so in this case, gradient of f and gradient of g vectors are either parallel to each other or anti-parallel to each other. Okay, so we will introduce a scalar lambda, which basically says that these two gradients can be related to each other. Okay, now what's the connection between these gradients and the scalar? We've introduced a new variable called lambda, and this lambda is called the Lagrange multiplier. Okay, now what we want to now do is to find out how do I actually go about solving a problem like this, and what's the connection to the Euler-Lagrange equations that we discussed in the previous class. Okay, so let's basically do a little bit of math. So we'll consider a simple case of a single constraint, that is we have only one constraint g, and we have the function f. We want to maximize this, or minimize this with the constraint g of x comma y is equal to 0. Okay, now let's basically start by determining the total derivatives of both these functions. Total derivatives would be, for example, dz by dx. That's the total derivative of the function f, and this will be del f by del x plus del f by del y times dy by dx. Similarly, the total derivative of g essentially would be del g by del x, where del is based here, and I'm writing down these are partial derivatives, plus del g by del y times dy by dx, right? So let's give some labels here. This is my equations 1 and 2 that I have, and I have got 3 and 4. Okay, now we can, if del g by del y is not equal to 0, it's enough for us. It's not equal to 0 as I go on this constraint contour. Okay, if that happens, then dy by dx will simply be del g by del x divided by del g by del y. Okay, and on the constraint contour, dz by dz, dz by dx, which is what we have already got from equation 3. We just substitute for dy by dx. That will be del f by del x minus del f by del y into this quantity here. What was it? Del g by del x divided by del g by del y. This is what I have, right? Now, this quantity, we have already said that this quantity z is equal to f of x comma y is effectively only a function of x that we want. Okay, so the solution to our problem, if z is effectively a function of x, then dz by dx is equal to 0 is obtained by solving the following equation. What is it? Del f by del y times del g by del y, del f by del x, sorry, minus del f by del y times del g by del x is 0. Okay, subject to the constraint g of x comma y equal to 0. So in other words, what we have done is we have basically replaced our original problem of solving 1 and 2 together to solving 5 and 6. So we want to impose this condition 5 with the constraint. We want to solve this relationship involving partial derivatives of f and g subject to the constraint of 6. Okay, so how do we do this? Algebraically, 5 and 6 is equivalent to determining the value of the parameter a new parameter lambda in order that the function of two variables will introduce a new function. It's an auxiliary function w so we have introduced a new auxiliary function. This function should have a stationary point. Subject to constraint g of x comma y is equal to 0. So let me just explain what we have done here. So we have basically we have said that here's a function z of x comma y, and we want to essentially treat this as a problem of one variable. Okay, and we can first take the derivative of z with respect to x. That gives me equation 3. Then we want to take the total derivative of the constraint as well. That gives me equation 4. And if we say that the partial derivative of g with respect to y is not 0, then we can find out the derivative dy by dx. Then we substitute this derivative into equation 3, and we basically got the relationship number 5. Okay, this involves partial derivatives of both f and g with respect to x and y. Now we have to impose this constraint. So if we can solve this equation 5 subject to constraint 6, it's basically we've got the solution. Okay, because why? because note that we are ensuring that the tangency condition is met. Okay, the tangency condition is exactly like what we had seen in the earlier case. So in other words, when the derivatives go to 0, then you have ensured a maxima or a minima, correct? In the same way, we want to, instead of basically just saying the derivatives are going to 0, the relationship between the derivatives in a specific form, that is equation 5, goes to 0. Okay. Now, the claim is that this specific form of equation 5 is simply can be easily satisfied by just defining a new auxiliary function, that is w. This w is nothing but f of x comma y plus lambda times g of x comma y. So we want to maximize or minimize this function f and the constraint g, and we have basically just written an algebraic relation between the two functions. We've just said this w now new function is f plus lambda g. The sign is not important, it could be f minus lambda g as well. Okay, now why does this ensure us that we will be satisfying the constraint constraint optimization problem? If you take the derivative of w with respect to x, it is nothing but del f by del x plus lambda del g by del x. And similarly, the wy is the derivative of w with respect to y, that is del f by del y plus lambda del g by del y. Okay. Now, if the tangency condition has to be met, so for this auxiliary condition, then all the derivatives of w has to go to 0. Correct? So that essentially, if we say that this w has a stationary point, okay, this function of two variables w, if it should have a stationary point, okay, that simply means that the derivatives of w has to go to 0. Okay, if wx is equal to 0 and wy is equal to 0, this essentially means del f by del x plus lambda del g by del x is 0, and del f by del y plus lambda del g by del y is 0. Right? These two relations can simultaneously be satisfied for any value of lambda. Provided this condition, equation 5, is met. Okay. Satisfied if del f by del x times del g by del y minus del f by del y times del g by del x is 0. Okay. This is what we have. So let me quickly summarize what we have seen so far. Constraint optimization problem. The constraint optimization problem is maximize or minimize f of x comma y is equal to constant subject to g of x comma y equal to 0. This is our original problem. Okay, this original problem is essentially can be replaced with a problem of a single function called the auxiliary function, which is define an auxiliary function. Okay, you can also call it the Lagrangian function. This is sometimes referred to as a Lagrangian function. This Lagrangian function is now a function of three variables, which is f of x comma y, let's say minus lambda g of x comma y. As I already said, the sign before lambda is not very important. We want to defined this lambda now. We have defined this Lagrangian function now, and we want to ensure that this Lagrangian function has now, after finding the Lagrangian function, defining the Lagrangian function, then our next step is find stationary points of this Lagrangian function L. The stationary points of the Lagrangian function L for us would mean that we have to find out where this Lagrangian function L has a maxima or a minima. How do we do this? This Lagrangian function has to simply satisfy the Euler-Lagrange equations that we had already derived in the previous lecture, right? So let's basically take up an example. This is an example that we've already shown there earlier. So here's the original problem. So we have find maxima and minima of f of x comma y, which is equal to x plus y, subject to g of x comma y is equal to x square plus y square is equal to 1. Okay, or g of x comma y is x square plus y square minus 1 is equal to 0. So you're on this plane f of x comma y is equal to x plus y, and we have to find out what is the maximum and the minimum of this function when you're on a circle, when you're traversing a circle, when you're going along this circle. So I'm showing with an arrow, that is g. So this is my g of x comma y, and the function itself f of x comma y is shown in color. Okay, now couple of things to notice here. Now you can straight away say that this is the maxima and this is the minima, as you can see, but we'll determine the coordinates of that. But I also want to highlight one more thing which I did not emphasize earlier. If you're at the maxima, note that the contours of f, is just this. These are the contours of f, right? Now there is a special contour which is exactly what I'm just drawing now. There's a special contour, and this special contour essentially becomes the tangent to the constraint g as well, right? At the special contour, the gradient of f would be like this. That's the gradient of f. And the gradient of g, the direction is not very important. In this case, the gradient of g, let's say, is like this. That's the gradient of g. Okay, note that at that location, the gradient of f and g are the same. In other locations, the gradient of g can be different. But exactly at the maxima or the minima, the gradient of f and the gradient of g are related. Okay, and the same applies in the other case. If you want to look at the lower part, let's say the gradient of g is the following. That's the gradient of g. And the gradient of f, on the other hand, is basically anti-parallel in this case. So the gradient of f and the gradient of g are basically parallel or anti-parallel to each other, and therefore I have gradient of f is lambda times gradient of g, exactly at the maxima and the minima. Okay, now let's take up this numerical problem. The idea is very following. The first step is create a Lagrangian function, that's f of x comma y, L of x comma y comma lambda, which is just f of x comma y plus lambda times g of x comma y. So in this case, it is just x plus y plus lambda times x square plus y square minus 1. That's my constraint. Okay, now this Lagrangian function is a function, and this is essentially, if you set Lagrangian is equal to 0, it is equivalent to f of x comma y when g of x comma y is set to 0. Okay, now the gradient of this Lagrangian function, this gradient involves 3 derivatives, by the way. Okay, what are the 3 derivatives? It involves derivatives with respect to x, derivative with respect to y, and we have introduced a new variable, that is lambda. Okay, this quantity is nothing but del L by del X, del L by del Y, del L by del lambda. Okay, we're just trying to find out the stationary points of this. How do we find the stationary points of a function? We set all the partial derivatives of that function to 0. This is exactly what we had done to determine, let's say, the maxima of this Gaussian. The maximum of this Gaussian f of x comma y is simply obtained by setting all the derivatives of this function to 0, partial derivatives, and it's a function of two variables x and y. Therefore, both the derivatives are set to 0 and we get the tangent plane. Similarly, we are trying to do exactly the same thing for this Lagrangian function as well, and this derivatives essentially would be del L by del X, that will be 1 plus 2 lambda x. Derivative with respect to this other one would be, and this, by the way, all the derivatives have to be set to 0. Del L by del y would be 1 plus 2 lambda y, and finally derivative with respect to lambda is simply x square plus y square minus 1. All of this is equal to 0. Note that we are treating the Lagrange multiplier lambda on the same footing as x and y. Okay. So we now have three relations. 1 plus 2 lambda x is 0. 1 plus 2 lambda y is equal to 0. And we have x square plus y square minus 1 is 0. That's a three relations for three unknowns. Unknowns x, y, and lambda, right? Let's basically, we can directly relate from the first two equations. We simply get x is equal to y is equal to minus 1 by 2 lambda. Okay, the first two relations simply give us this, and we don't want lambda to 0. If lambda is 0, we will not be able to impose the constraint. Okay, and from the third relation, we simply have x square, that becomes 1 by 4 lambda square, y square 1 by 4 lambda square, minus 1 is 0, and therefore I have 1 by 2 lambda square is equal to 1, or lambda square is half, and this gives me two values for lambda, plus or minus half. And therefore if lambda is plus half, then x is equal to y is equal to minus 1 by 2 times lambda is 1 by root plus or minus 1 by root 2. Okay, so now I have 1 by root 2, and that simply gives me minus 1 by root 2. Okay, x and y gives minus 1 by root 2, and if lambda is equal to minus 1 by root 2, then I have x and y both are equal, and they're equal to 1 by root 2. So now I have the coordinates of the 2 points here. The coordinates of the 2 points are stationary points of L. L is 1 by root 2 comma 1 by root 2, and for a value of lambda which is minus 1 by root 2, and the other one is minus 1 by root 2 minus 1 by root 2 with a value of lambda which is 1 by root 2. Okay, so you can clearly check that these quantities, so these quantities 1 by root 2 and 1 by root 2, what do they correspond to? If I were to clear all of this here on this figure, so the first point corresponds to this fellow is 1 by root 2 comma 1 by root 2, and the other point here is at the bottom. This point is minus 1 by root 2 minus 1 by root 2. These are the locations. let's confirm that they satisfy. I would like all of you to try and confirm the g of 1 by root 2 comma 1 by root 2 is simply be x square plus y square minus 1, and that's my g with x comma y equals 1 by root 2 comma 1 by root 2. And you can clearly see that if we substitute this, x square plus y square becomes half plus half, that's 1 minus 1, and this goes to 0. Implies this quantity is on this point is on the constraint, and our the original value of the function f of x comma y, which is x plus y, okay, is simply now 1 by root 2 plus 1 by root 2, that is 2 by root 2, or this is just root 2. Okay, and similarly at x comma y is minus 1 by root 2 comma minus 1 by root 2, f of x comma y is just minus root 2. So we've actually got the values of the function at those two locations. So at the bottom you have f is equal to minus root 2, and at the top f is equal to plus root 2. So we've got the values of the function at the two locations. We've ensured that we are also on the constraint function by checking that g goes to 0. Let's quickly recap what we have done. The moment we have a function that we have to maximize or minimize subject to a constraint, let's say call it g, then we define a Lagrangian function, which we call it, we can call it as L. This Lagrangian function is now a function of three variables, that is x comma y comma lambda, right? This Lagrangian function is simply the algebraic, it's written in a simple algebraic form, f plus lambda g. It could be f minus lambda g as well. Now what we then want to do is we want to look for stationary points of this Lagrangian function. The stationary points of this Lagrangian function for this simple problem is just the all the partial derivatives of this Lagrangian function has to go to 0. So we just take the derivatives of this Lagrangian function and then we set it to 0, and then using this algebraic relationships that we got, we simply determine the functions determine the values of x comma y at the maxima and x comma y at the minima. Okay. It's a very powerful technique, because what it allows us to do is, if I have a constraint optimization problem such as the shape of a sessile droplet subject to a volume constraint, in this case we want to write down the energy functional, that is energy functional is my capital E that we had already written down in the previous lectures, and then we want to impose a constraint of volume, right? The volume is another constraint, and we want to now define a new function like a Lagrangian, or Lagrangian functional. This Lagrangian functional is basically going to be related to the total energy and the volume through this Lagrange multiplier. So we just have something like E minus lambda times V, where V is the volume and E is the energy. Okay, so we'll use this very powerful technique of the method of Lagrange multipliers to solve a few interesting problems in capillary statics. We'll first look at the problem of the shape of a sessile drop, and then we'll extend this to the shape of a large puddle which is also subjected to gravity. I'll see you around in the next lectures. Thank you.